thank you to Sofheim for inviting me to talk. I think when I started out, it was quite a long time ago now, I won't say exactly how many years, I was studying zinc modulation of glycine receptors being close cousins of GABAA receptors. And so I think maybe just because I'm not a very adventurous person, I'm still doing kind of the same stuff now, 20 years later. And so if we think about GABA receptors then, I'm glad to be sort of flying the flag for pentameric ligand-gated ion channels because I don't think they've been discussed yet as a topic. And obviously because they're ligand-gated ion channels, then the key feature is that they bind a chemical and convert it into a charge effect across the membrane. So in response to an action potential, GABA is released, binds to GABAA receptors, and then they open an intrinsic channel, and GABAA receptors are inhibitory. They have a chloride conductance, and so you get this rapidly activated IPSC, which decays as GABA is cleared from the synapse. And so I guess just sort of building on that then, GABA receptors are they're the main inhibitory sort of force for synaptic inhibition in the human brain. And I guess you think of neurons as kind of calculators with a certain amount of glutamatergic input and GABAergic input, and it's summated through time and space to determine whether the neuron fires an action potential. And GABA receptors kind of sculpt the excitation and sort of help keep the brain from becoming too overexcited. And so anything that is, say, a positive allosteric modulator against GABA receptors will help spread calm through the brain. And so there's the nice thing about GABA receptors is lots of different subtypes, and Mother Nature has kind of very conveniently split them up into sort of having different roles in behaviour. It's not an absolute segregation. There is some overlap, but sort of alpha 1's been linked kind of to sedation, alpha 2 to anxiety, alpha 2, 3 kind of to pain, maybe itch, alpha 5 to cognition. And then there's some key drugs such as, the benzodiazepines like Diazepam, Valium for anxiety, and Zolpidem for insomnia, which is a non-benzodiazepine, and they all target this alpha site at the alpha-gamma interface. And as someone who's very biased and a proponent of GABAA receptors as therapeutic targets, it's very nice to have seen over the last 10 years that there's been a lot of high-profile papers implicating GABA receptors in various different disorders: autism, stroke, pain, cancer, even diabetes. Adding and building on the ones where we already have indications for treatments. And maybe when I was a bit more naive and I guess excitable or whatever, I kind of imagined that I would one day go on to sort of be involved in developing loads of really cool ligands to target all of these kinds of things, and I would create sort of a cocktail of drugs which could be taken as a kind of panacea that we could use to make a kind of a superhuman who would be like a GABA man, woman, I should say. I should put kind of woman in there, I guess. That would be intellectually enhanced, never stressed, never feel pain, and could eat as much candy as they wanted without ever getting diabetes. You probably wouldn't get into an Avengers movie, but still pretty cool, I reckon. So that's ultimately my sort of goal that I'm going to try and work towards for the next as many years as I can keep an academic job. I think there's been obviously over this time there's not really been any drugs that have sort of made it through. There's been one neurosteroid that came through last year, but I think one of the things obviously that could really help is having structures and a molecular basis, a kind of molecular understanding of how these drugs work to kind of at least sort of build structure-activity relationships and be able to develop new drugs. And my supervisor of my previous lab that I left about a year ago when I started setting up my own lab has published some very nice structures. There's been a few others out as well, but these are sort of the best resolution ones, maybe the most reliable, which get to around 3 angstroms. and they reveal, for example, one of the structures reveals the binding mode of Diazepam, which you can see here, and you kind of get an idea for the kind of density, and they can fit Diazepam into the pocket. But nevertheless, this structure, I mean, this protein behaves really well, but at the moment we're a bit kind of limited because it depends on a protein that binds to a kind of nanobody, and you can kind of see that here in the averages, which helps the particles to tumble, and also is really critical for aligning the subunits over each other. So you put the alphas on top of the alphas and the betas on the betas. So it's not possible to, at the moment at least, get high resolution structures of all the other subtypes. And so something that I began quite a few years ago now when I was in my old supervisor's lab was I was looking at crystallography at the time, and I went on a big engineering project, and this was just before sort of cryo-EM sort of kicked off. So I mean, I'll be honest, if cryo-EM had just come out a little bit earlier, I wouldn't have poured all of my effort into this. But having said that, it still has sort of generated data which I think is useful. And so I'm not going to go through all of the various mutations that I made, but essentially I tried to make, so this is a native receptor, it's got 2 betas, 2 alphas and a gamma, and I tried to make a kind of a homomeric form with 5 alphas where you change one side of the interface to be like the gamma subunit, and I had a slightly different one which was a heteromer where you have a single whole gamma subunit and then 4 alpha subunits. And so the idea was to recreate the benzodiazepine binding site and in a way in which you could sort of have, I guess, a kind of generic platform for understanding how drugs bind to this binding site. So you could easily then mutate residues across here to make it any alpha subunit, any gamma subunit, maybe even switch to delta to understand drugs at this pocket. And so for the homomer, the homomeric version that I made then, the benzodiazepines, they didn't bind that well. They're still okay, around 1 micromolar. And you can see here the binding curve. So this is 2 different types of benzodiazepines. You've got the traditional ones, which have this pendant phenyl ring, and the imidazopyrrolo ones, such as flumazenil and bretazanil. So flumazenil is like a neutral ligand, so it's actually an antagonist used to treat benzodiazepine overdoses by, say, Valium. And for both types of ligands, it's quite a bit lower, maybe, say, 100-fold. I won't get into the sort of precise details, but somewhere in that region. And in the case of the sort of the semi-heteromeric protein that I made, so you have this one site here, which is a bit more realistic, and then you also have homomeric sites going around. But if you knock out these sites, you just look at this one specifically, then the affinity was better, more towards the wild type, within 5 to sort of 20, 30-fold, but still not quite as good as the wild type. But these proteins behave really well, actually, and they crystallize really easily, and you can get structures easily, and the data processing is a little bit tricky. But generally, the maps are pretty good quality, and you can fit the ligands into the non-protein density with a good degree of certainty. And so we can, so we've got the binding modes for both of these, and actually at the time there was a cryo-EM structure with flumazenil bound, and despite having obviously a lower affinity, the binding mode was almost identical to what was done for the heteromeric protein, which was at a lower resolution. And if we compared the heteromer for this heteromeric site versus the homomeric sites, and we map the binding of bretazanil over the top of each other, then the binding is kind of indistinguishable. You can't really pick it apart. So it seems like even though the sites of the homomeric protein are lower affinity, they still seem to have pretty much identical binding mode. There's no obvious differences in the binding. And so one interesting thing was that this conformation of this protein was kind of like represented a kind of activated conformation. That was kind of the closest that the protein was to around this binding site. And I guess the question is, flumazenil is a neutral ligand, whereas bretazanil is a potentiator, and this is just a kind of demonstration. I didn't generate these curves, but bretazanil will potentiate. Flumazenil, if you add that as well, will then block the bretazanil effect. It's not actually an inhibitor of the GABAA, so it's just pure antagonist, not an inverse agonist. And then the question is, I guess, so the conformations were identical, just some very slight differences maybe in this histidine down here, but nothing to really explain why one is a neutral and one is a potentiator, because the conformations are the same. And if we look at the structure then of this heteromeric GABA receptor that was solved, one of the things that we know is that the subunits rotate when they go from the resting state to the open state, so they're all rotating in this kind of anti-clockwise direction, which you can kind of see here. And interestingly, in the presence of the diazepam, it doesn't seem to, they solve structures in the open conformation with and without diazepam, and there's no obvious structural effects. So diazepam itself isn't inducing anything. It's kind of like just acting as a kind of molecular bridge between subunits. And so kind of going back to our structures, then we can kind of say, well, if the protein already favours an activated conformation, then the neutral ligand would be able to bind because it's happy binding to an open or a closed state, it has no preference. And the potentiator could obviously bind to that same conformation because it's a potentiator. And so what is the difference then between these molecules that might make one prefer the open state over the closed state? And obviously there's a few different differences between the molecules. But there was actually a study, a pharmacology study that was done on a couple of other ligands. These are both also related compounds. And you can see the only difference between these two is this key methyl, trimethyl kind of entity over here. And one of these compounds, this one was a potentiator, and the other one was a neutral ligand. So it seems that this is the key region. And if we look, so we can dock this, and it overlays with the protazenyl very well, and we can see the trimethyl then is key as is a key area, sort of bridging between this loop C, which we see over here, loop C, and the neighbouring subunit. So it's increasing the contacts in this region here, and this region narrows in the activated state. So we can make quite strong assumptions, quite strong predictions then, that the reason that this protazenyl is a potentiator is due to this extra group and these extra contacts that it's mediating here, kind of helping it to be a better kind of glue for the open conformation. And so more recently then in the lab, since I've just set up the lab, we've been getting the cryo-EM up and running. So we did a bit more on this, on the homomer, a slightly different version, which has got a slightly better pharmacology. And actually this works really well in cryo-EM. It's really robust at giving structures. You get really nice density where you can clearly dock. And this is diazepam that we did in this case. And again, the diazepam binding mode for our homomer, which has got a lower affinity, is identical to the cryo-EM structure that was solved before. And with a relatively few particles, and even this was using a cryos, but we also did use the less powerful, smaller brother, the Talos Arctica, similar number of particles, and we could get exactly the same quality of resolution. And it should be relatively easy to simply mutate out the relevant residues to switch between subtypes. And so I think this offers a simple, kind of robust platform for understanding how drugs bind between the various different subtypes of this pocket. So that's something that maybe could be of use for kind of structure-based drug design in the future. Nevertheless, obviously small molecules, they have a limited interaction interface, and the primary ones in the brain, they all contain gamma-2, so they're all the same on this side. And then on the other side, there are some differences between residues, between the alpha subunits, but nevertheless, it is tricky and challenging to get selective ligands at this benzodiazepine binding site. And so originally when we were working on producing GABA receptors, we sent some off to a collaborator who injected them into llamas, and he raised nanobodies. So we originally did this to help with crystallization, and this worked really well. The nanobodies bound to our GABA receptors, mediated clear crystal contacts, and we were able to get structures, for example, this one with neurosteroid bound. But one thing we observed was when we were doing a biocore, and we were looking at how well the nanobodies bind to the GABA receptor. For some of them, we could see that they had clear favorability, where they had a higher affinity of binding when GABA was bound to the receptor. So this suggested then that these nanobodies prefer binding the open state of the protein and maybe would be potentiators. And in fact, this nanobody was the one that was used to solve this cryo-EM structure, so you can just see it bound here. And when we looked at this in terms of electrophys, then we could see a very nice potentiation, and this is Diazepam potentiation here, this one. So the kind of efficacy of the nanobody was actually very strong. It gave a significantly stronger amount of potentiation than Diazepam could give, and less sensitivity at higher doses. You actually could get direct activation by the nanobody on its own. You can just see this in some of the recordings here. And also, it was unlike small molecules, even though it was a very powerful potentiator, it was completely selective up to 10 micromolar for the alpha-1 subtype. And so I guess sort of one question is, there's only one of these binding to one subunit, and Diazepam also only binds to one subunit. So, why is the nanobody so much more efficacious? But we also had another structure that we'd solved. This was to lower resolution, and this has got 2 nanobodies bound. So if we went up to a higher concentration with the nanobody, we could get 2 of them bound to 2 interfaces. And so what we can suggest then is that these nanobodies are a bit more akin to how the anesthetics work at GABA receptors, because at the higher doses you can get direct activation, and at the lower doses you get potentiation, and you have more than one molecule binding, which would be, say, more like neurosteroids, where you have two molecules of pregnenolone binding to the receptor rather than Diazepam. So the higher efficacy could be related to this, the kind of a bit more like anesthetics, but completely subtype selective, whereas anesthetics have no subtype selectivity whatsoever. And one of the other things to point out is the affinity for the purified protein when we were doing the biocore was like 10 nanomolar, so it's very high. The affinity in electrophysiology was much lower. It's about 10 micromolar, so it was a 1,000-fold shift. So, why was this affinity for the nanobody so much lower in electrophys? One possibility could be that there's some kind of hindrance from the membrane. So this is the nanodisc, and the nanobody or megabody, as this one was called, binds underneath. It binds quite low down the extracellular domain, and maybe in cells you have more hindrance, which dramatically reduces the affinity. We could also understand the basis of the selectivity, and so we can see, for example, that there was a glycine in alpha-1, which is a glutamate in all the other subtypes, which points outwards from the loop C and clashes with the nanobody. And then we also tested in slices, and this is Diazepam versus the nanobody, and we could see that we got a very, very strong potentiation of the IPSC, so the nanobody can get into the synapse, it can bind to the physiological receptors. This was for hippocampal slices, and you get this very strong sort of extension of the decay, and you also can see a kind of possibly persistent current, or it could be that the IPSCs have just been sort of extended to such a significant degree. And then this is just a table kind of summarising that, this key one here being the area under the curve, which is much higher for the nanobody versus the Diazepam when we're trying to sort of match the doses roughly, sort of EC70. And I'll skip this last bit and I'll just say then, so the nanobodies then, they bind a much larger surface area interface, which allows them to be more selective because there's more chance they're going to hit an epitope. And just acknowledge people, obviously my old supervisor Radu and Simonas, who's helped me set up the cryo-EM. And this is my lab at the moment, Vikram, who's been helping me get the cryo-EM up and running in my new lab and to get the structures. So.
Thank you very much, and thank you again for staying on time. That's excellent. Questions? Yes.
Hi, Paul. Very nice talk. Looks like an exciting direction. In the recordings in the native cells,
Yeah.
Was it hippocampal neurons or?
Yeah, sorry, that was dentate gyrus granule cells.
Okay. Did you try in an alpha-1 knockout mouse?
No.
Because you should have no effect then, right?
Yes,
Because there's probably multiple GABA receptor combinations there,
Yeah,
like any neuron,
yeah.
and it'd be nice to show that. Anyway, something as a thought.
Yeah, is the alpha one viable? I don't know.
Yeah,
It is.
yeah.
It is. Okay. Yeah,
We've
good.
got it if you want it.
Okay. Right, yeah.
It's got a Canadian accent though.
Just
There's
send it
enough.
to the host. It's all right. We will unfreeze it. And,
More questions? Oh, yes, up there.
Thank you. Lots of different subtypes, as you said, to choose from. Have you thought about looking at the extrasynaptic GABA receptor combinations to see how they may vary?
in what context? Sorry, in terms of the
So
nanobodies, or in terms of the drug design, or the structures, or do you mean?
Understanding, yeah, how they differ from the synaptic forms, such as the brain heteromer you've highlighted here.
Yeah.
If you have a delta subunit in there,
Yeah.
for example, or eta, how that looks different.
Yeah, no, we haven't done that yet, but obviously that's something to definitely do in the future.
Can I just have a quick question? Naively, are you suggesting that these nanobodies might be useful as therapeutics?
That would be my hope. Yeah, so one of the things I want to do is try and conjugate them with other proteins to get them across the blood-brain barrier.
Okay.
And so obviously I'll do some testing in animals to see if I can go in that direction and validate these nanobodies before I take them too much further in terms of their pharmacology. Actually show you could use them in a whole animal.
So you'd
system.
want ones that weren't such high affinity as the sort of ones that you're showing.
You'd want very high affinity.
You would?
Yeah, for the nanobody
I mean, they
part,
would be
yeah.
irreversible, wouldn't they? That wouldn't be a very...
Yeah, I don't know if it just sort of sits there in the background. You have low occupancy of a
okay.
certain subset of GABA
Well.
receptors. I think it could still depends what they do, but I think it could work.
Any more questions? If not, thank you very much.